Hello, welcome to this crash course in functions. Let's go through and review everything about functions really quick to make sure we've got you up to speed on that. We start out first with relations. Now, relations are anything that connect two data sets together. You could have something like in Hawaii, the days in May and the average temperature on that day. That's just connected two sets of numbers. You could take the average temperatures in any month of the year and you're connecting a month, the January, February, all the way through December, with numbers. So it's anything that relates data with very few restrictions at all. So let's take one that I often use in my class. I'll poll the class and say, okay, how many of you have a birthday in January? And they'll tell me, oh, there are 3. And then how many in February? There are 4. All the way down through December where we got 2. So you'll see we've just associated the months of the year with numbers from 0 up to 5. So we'll put parentheses around them like this. Putting parentheses around them like that links them together and connects them. And so we've got the months of the year, months, and we're connecting them up with numbers from 0 up to 4, 5. There we go. Yeah, this set of numbers here. And so when we have that set of numbers and we connect them, we have related them, which makes a relation. Well, the first set, so if we were to play a game and said, okay, what number is associated with May? You'd say 1. If I said April, you'd say 2. And as long as we put this in the first place, this guy is called the domain, and that guy is called the range. And that's it. This is the first set, that's the second set, and we link them up like that. That's all that I have to do with relations, domain, and range. So we could play this game November 5, December 2, stuff like that. So that's what a relation does. Now, if we want to get a little bit closer, there's a special kind of relation that is called a function. For example, let's take this exact same data set and switch it around a little bit and make the domain and the range switch places. So it looks like this. Good, now we switched them around. Now watch how we play the game. We say 0, and what comes out? Certainly March comes out. 5, you look down here and you see 5, and that gets mapped over here to November. Now if I say 2, all of a sudden we're like, oh shoot, what just happened? 2, some say April, some say June, some say December. And we realize that this relation, relating them this way with the domain where it's got a repeated domain here, on like 2s or 3s, that causes a problem. In math, we want to be able to stick something in and have it pop out an exact answer. Like in a calculator, we plug in a problem and it gives us one exact answer. Here, we would plug in something and it would not. So some relations, like this, when you organize it this way, have this property that it will always give you exactly one answer for every problem you stick in. Others don't. And that's kind of problematic in that sense because we can't associate exactly one answer with sticking in one input. So when they do that, these guys right here are called functions. And that's the only thing. You can look at it and see a function really quick. Do any of the domains repeat? Nope. And so this guy's a function. This guy, do any of the domains repeat? Yep. Right there, there, and there. That means that if we stick in 2, it will not give us a specific answer. There will be many of them. And so that is not a function. So I'm going to circle this guy here. And that guy is not a function. Even though he's a relation, relations can do that all the time, but he is not a function. Let's see what this looks like on a graph. Let's put these two on the graph here. So we're going to take this guy and graph him like this. Put the months down here, the X, that's our input. There we go, June, July, January, February, March, April, May, June, July, August, September, October, November, December, and 0, 1, 2, 3, 4, 5. Good. And as we graph them, January has 3, so that would be a point there. February has 4, which is right up there. March has 0. And there we have a graph. You'll just see it. We plotted them along here, and that's it. That's what it looks like. And at every, like April, you'll see ping right here. April has exactly one dot above it, meaning that when you stick in April, it comes out just fine. Now let's graph this green one and see what it has. This guy will have 1, 2, 3, 4, 5 down on the bottom, and the months up here. And there we have the months, January, February, March, April, May, June, July, August, September, October, November, December. Great. So now let's put these guys on here. And I'm going to do this a little bit slower. So 3 goes to January. Good. 4 goes to February, and you'll notice that 4 goes to, what's the other one? August. So right here. Now notice what happens, and this is where we have a repeated domain element, and it ended up that these guys, because they were two outputs for the same one input, that a vertical line hit both of these. You have 2 points right above here, and that made it not a function on the 4. Let's go back and look at the other ones. So 0 for March. I think there was only one of those. 0 for March was right here. Good. And then 2 for April, but 2 was for April, June, and December. So when we put those on, 2 was for April and June and December. So that vertical line had crossed 3 points. And that's the distinction. That's what makes it not a function. So the relation can be graphed without any problem, but as soon as there are 3 points on the graph where a vertical line would touch it, that means that this one input has 3 different outputs, and it's not a function. That's kind of cool. So let's look at some algebra examples that you guys are really familiar with. Let's do something like y equals mx plus b, like 3x plus 2. When we graph that guy, we have 0, 2, and the slope is up 3 over 1, and it looks like this. Now, if we passed a vertical line through here, you'll notice that it never crosses that line twice. Yeah, that's a function. That's exactly right. And that's why we use that function notation. Now we'll do another one that you guys should be familiar with, like x squared plus y squared equals 9. If you're not, let's try a couple of points. If you're not familiar with how to graph this guy, if you let x be 0, then y could be a plus or minus 3. Both of those y squared would equal 9 plus or minus 3. So you see it gets right there and right there. Well, you can automatically tell, based on what we did before, this will not be a function. This is a circle. If y is 0, x is plus or minus 3. Yeah, it's a circle of radius 3. Oh, I just drew a perfect circle there. But you'll notice that each time on the graph, a vertical line goes through and hits it at 2 points. That means this one x value has 2 y values. And you can see that algebraically. If we try to solve this for y, subtract x squared, y squared equals 9 minus x squared, and then square root both sides. And what do we have to do when we square root? Plus or minus. So this is y equals square root of 9 minus x squared and negative square root of 9 minus x squared. Yeah, you can't solve it for y, so that's why we won't use this functional notation. That right there is not a function. Well, what are common functions in? Well, polynomials, like if you have f of x equals, x squared plus 3. You guys remember what that guy looks like? That's a parabola that's lifted up 3. And if you look at that, yeah, that's going to be a function. And we're able to use the f of x notation and say, yes, f of 2 is, we stick that in and we stick 2 plus 3. Oh, good. And that'll work. So let's see how they work algebraically. Let's stick in a couple of different things with functions. On f of x equals x squared plus 3, if you were to do f of 2, you do 2 squared plus 3. This 2 goes in where the x is. Perfect. And we get 2 squared is 4 plus 3 is 7. So f of 2, it's like a machine. You stick 2 in here and it shoots through the function. Bam, hits the range. 2 gets 7. So this is the point 2, 7. And it's just like what happened at the beginning when we're playing a game. I stick in 2, it pops out 7, just like a machine, a Xerox machine, if you will, or a bow and arrow. You'll notice you shoot 2 as part of the domain and it hits downrange and hits the 7. Well, here you shot one arrow and it tried to hit 2 things. That's kind of weird. What if we did f of negative 2? It's great. So this is negative 2 squared plus 3 equals 7. So negative 2, 7. Notice that even though these 2 points hit the same thing, that's still okay. It's still a function. Just like over here, 2 months could have the same value, but they have a very specific value, so it is definitely a function. All right, let's use this notation a little bit better, and let's see if we can do what is f of m. I don't know. You stick m in there. M squared plus 3. Look at that. What about f of Bill? if this is really a machine, you just crank Bill into there and you get Bill squared plus 3. I don't know what that ends up being. Yeah, I don't know if Bill is really part of the domain here, but let's keep going with it. Now, this is one that's kind of fun. What if I stuck in f of x plus h? Stick it right in there. You take all this x plus h and you stick it right in there. We're operating on that, so we have x plus h squared plus 3, which means we could multiply that out. X squared plus 2xh plus h squared plus a 3. Now, there's a common mistake, and I'm going to write that on here. Look at this. Mistakes. Some people will stick that in, and they'll do f of x plus h as, f of x is x squared plus 3, and just put an h on there, and then do plus 3. That's bad news. You got to stick the whole x plus h in. Yeah, you got to stick that whole thing in where the x is. And that's what helps you to get the proper output when you stick in x plus h. Now, one last comment. When we do inverses on functions, that's when it goes backwards. Notice that when we took this little month and number thing, when we tried having it go backwards, undo the relation, we were having April gave us 2 and June gave us 2 and July gave us 3. When we switched them, it didn't go exactly backwards. Now here, if you wanted to do the inverse on this one, this top one here, this is the y value over here. If you want the x and the y to switch places, let's switch them. And you get x equals 3y plus 2. Doing this, switch the x's and y's. Exactly. So this would be, switching the x's and y's will give us an inverse. And so when we get y by itself, subtract 2, and then divide by 3. Yeah, so what is that guy? F inverse with a little negative 1 up here of x equals x over 3 minus 2/3. And you know what's amazing about this particular thing is it's this guy. Let's erase a little bit so we can see it a little clearer. So f of x equals 3x plus 2. So that's like this, and it goes kind of like that. There we go. So there's the original function. Now what's interesting about this one is going to be the inverse is going to be at negative 2/3 here, and it's going to have a slope of 1/3, up 1 over 3. So it's kind of more of a shallow slope. It goes like that. You're like, whoa, what just happened between these two? And this is an amazing little connection here. What it did is it took this point right here and made it the point 0, 2, and made it the point 2, 0. And this point, which was, looks like negative 2/3, 0, made it 0, negative 2/3. It switched all the x's and y's. So graphically, that switches it along the line x equals y. So this guy popped from here right down to over here. And anytime it crossed that line where x and y were the same, it kept it exactly the same. So graphically, that's what inverses do. Okay, that should give you a little brief review of what functions are and how they work. Good luck.